Hi everybody, welcome to Pre-Calculus. Happy or good morning, y'all. So it is October 28th. We're nearing the end of October, and we're also learning a lot. So here's our quick attendance check-in question today. And it's trying to be like, Halloweeny, but would you ever go to a graveyard at night? Is the question for our attendance check. Let's go ahead and answer that into the chat, and then all right, we got a few here. Some yeses, some nos. Mostly nos are winning right now. And then, well, yes, if you're in a group, and there's some who are yes. Let's say, yeah, if it's in a group, okay. We have a bunch that are like, we have more that are like, yeah, in a group. All right, so now the yeses are kind of winning the nos. Oh no, that would be scary, Jaleel. If people start disappearing one by one, now that's scary.
Well, duh, it's Halloween. How would you want it? Even though everybody's gonna be okay at the end.
Not in real life. In a movie, sure, that sounds good.
No, no, no. I meant like if you guys plan something like that.
Yeah. Oh, no, no. I doubt we'd plan that, but yeah. All right, y'all. So let's see. So I know I have a few of us still logging in. Give me a second so I could go ahead and let y'all know who I'm missing and whatnot. Welcome everyone who just came in. We were doing this attendance check question, which was, would you go to a cemetery at night? And then I'll let y'all know who I have absent. Cool. Yeah. So as for me, if anyone's curious, I would only because I guess I'm not superstitious. I don't know. Like I'm not gonna think people are gonna come out of their graves and whatnot. So that's for me. Actually am okay walking there at night. I would think that's a peaceful walk. That's me. But all right, let me go ahead and say who's absent. Let me know if it's wrong. So let me know if I missed you because I'm basing it off the question, and also like if I quickly got you um, as you were logging in. So here's what I'm missing: Kalia, Justin, Shakira, Rainey, Anna, Jose, Jonathan, Jimena, Amara, and KK. So that's who I'm missing. We actually got Anna right now, so let me fix that. So please, if I said one of your friends' name, please let them know to come on in because we will be having some credit activities today. So I'm definitely trying to boost the credit that I'm giving in class so that our grades are not just asynchronous work. I want to make sure I'm capturing all the thinking and stuff you're doing in class too. So it's like I noticed that I was only recording like asynchronous work the first time around. I think that's not fair because some of you didn't get the awesome work and contributions you were doing in class. So that's why I want to strive to give you all more credit like during class. All right. We now have Jonathan. Awesome. So yes, please continue to text your friends if they're not here. So I could go ahead and fix up this attendance. Let's get on with it though, everybody. So here we go. Here's our agenda. So we just had our attendance and check-in. We're going to be finishing up our notes, so you definitely need your notes. So notebook, or if you're doing digital notes, either one, you want to make sure that's ready. And yes, we want to take notes. So you got to write stuff down when this part comes. After we talk about right Riemann sum, we're going to have a Google Doc participation. So that's where the credit's going to come in today as well. After that, we're going to have notes on connecting the Riemann sum to sigma. So that's going to be a new big idea. We're going to make that connection. And then at the end, we're going to have a checkout. Sorry, I was laughing because this was for my yesterday class. Asynchronous 12 was due last night. So that was due yesterday, last night. The next one is gonna be due Thursday night, and it should be posted. I think it is. Not sure. right? Or am I lying? Yesterday? Yeah, asynchronous 12 was due last night. Yeah. And I still need to post a new one. But anyways, yeah, so that's just an update on that. And another thing is please jump into the office hours if you need help because a lot of you have been bringing in like your assignments and I've been helping you one-on-one with it. Like totally, you would still get like full credit and all of that. So don't worry about that. Also, if you're turning in anything late, please text me, send me an email so I could go back and check it. Yeah, and then we got rainy. Awesome. Oops. Okay. All right, let's get on with it though, y'all. Okay, so before we start our notes, I'm just gonna kind of remind you all our learning target. So we wrote this down last time, so you don't have to rewrite it again. This was last time's note. This is me just refreshing you on what we did. So last time, our goal was to estimate the area under a function. Specifically, our learning target is I can explain how to approximate area under a function using this new thing called Riemann sums. And we did Riemann sums, which look like this. So this is my recap. So remember, what we started off talking about was something called the left Riemann sum. And let me remind you all why this is called a left Riemann sum. It's because the upper left-hand corner of the rectangles that were drawn are touching our graph. And our graph is represented by this black line right here. And it's also written right here in function form. Now, we did have an exit ticket about this, where I had you all fill out that exit ticket. If you did not get that exit ticket down, you're missing your credit. So just make sure if you did not get that exit ticket credit, check Power School because you want to make sure you reach out and do that exit ticket. So as a reminder, I feel like I was missing like 5 or 6 exit tickets from this class from last time. So it's not too late to get that in. But anyways, um, the next part in the process was in order to find the rectangle heights, which were right here, we had to use our function to find the rectangle heights. Not only that, but we had to use the inputs. So basically we had to use the x sub 0, we had to use x sub 1, we had to use this one, and then lastly we had to use this. The end of all that, we did base times height. The bases were all the same in this case. The bases were 0.5. And then all we had to do was multiply by those heights that we had just calculated right here. Those heights are right here. After all that, we went ahead and added it all up. So this is me just recapping what we did last time because today we're going to move on to the right Riemann sum. So this is my recap. Let's see what's in the chat. Oh, these are private chats. Can I get the exit ticket? Yes. So actually, if you could send me a text on reminder email, it's better because I'm not able to pull it up right now. That way I could send it to you right after class so you get your credit. So again, exit ticket credit, please send me a text on remind or an email and I'll send it to you. Yes, for sure. You're welcome. All right, let me clear this up so we could talk about the new thing. Again, you're not copying this one down because y'all should have this from last time. And if you need the recording, I'm happy to share it. But let's go, y'all. So this is the part you want to write down. This is also the part that you're going to have, we're going to do the Google form participation on. So you want to make sure that you pay attention. We're now going to talk about right endpoint rectangles. Before I start talking about the right endpoint rectangles, I want you to go ahead and draw this image. So it's different actually. It's not the same image that we were working with the other day. The only thing that's the same though is the function is going to still be y equals x squared. We're still talking about the same function. And the other thing that's the same is that the widths are still going to be 0.5. Down here, they're still 0.5. The only thing that's different now is you all have to make sure that you estimate the heights well. So this is, I think that's at 4. And I think this is going to be slightly above 6 or something. Whoops. You know what I mean. So just make sure that you make your sketch accurate. I'm just doing these dotted lines so y'all can see. So I think this third rectangle goes a little bit above 6, The fourth one appears that it hits exactly at 4, and the first one hits exactly at 2, and then the last one hits at 9. So this one actually has less of like decimals, and it's more like whole numbers in these rectangles. So first sketch that down, and then I'll talk about the general qualities of this. So let me give you all like a few seconds. So please sketch this down. Again, you want to make sure that your notes are complete because this is going to help you out. All right, so don't worry if you didn't have enough time to fully sketch this because I'm still on this slide. I'm just going to start making bullet points and start talking about this. But yes, you want to make sure you have this drawn well, nice and big maybe, because we're going to be doing some work with it. We're going to be doing the same process we did, and we're going to find the area of these rectangles. But before that, one thing to notice, which I already verbally said, but I'm just putting it here as a bullet point, is notice that the base is again 0.5 units. Um, Again, you can change the base width depending. So if you were to draw your own rectangles, you could choose whatever width you'd like, just so you know. But because this is already given to us in a picture, we're determining that it's 0.5. It's given to us, so we're just using it. Next. Now, notice why these are called right endpoint rectangles. So again, very similar to how the left endpoint is defined, but in this case, notice that the upper right-hand corner of each rectangle is the one that's touching the line of the graph. So now I'm circling those points right now so y'all can see that. So the upper right-hand corners are touching the graph, and that's why this is called a right endpoint rectangle. You can also call them right Riemann sums. Let me go ahead and pause here now to allow you to get down these bullet points for a few seconds. Again, slides are posted in Google Classroom though, if you need to go back. All right, I hope you all got that down. Let me clear up this slide. So I'm going to clear all my drawings, and then we're going to go ahead and jump into doing the calculations. Hopefully it's not as confusing because we're doing this again. Like we did it with the left, now we're doing it with the right. All right, so here's our graph that you have copied down. And again, notice that I labeled each of the endpoints here with subscript notation. So that's what the subscript notation is. Again, it's very useful to do that, especially in this case, because it helps us organize which endpoint we're using. So notice that for this particular function, let me use the drawing tool. For this particular function, the first rectangle height is right here. It's the first right endpoint, see, right here. And I want you to notice that it corresponds to the point 1 sub 0. Corresponds to this subscript. And we also know that it's right in between 1 and 2. And we know since the width is 0.5 that this point right here is 1.5. So there's just some things to notice there. So basically we're not using this one here. We're not using x sub 0 at all because that's not a right, an upper right hand corner point. So we don't care about this one. Then notice that the next upper right hand point corresponds to 2, which also corresponds to this subscript notation. The third one corresponds to, and it's between 2 and 3, so that one's 2.5. And again, it corresponds to this subscript notation. Lastly, the last upper right-hand corner that's touching our graph is right here, and that's going to correspond to the number of 3. And the subscript notation it corresponds to is x sub 4. So I'm just like pointing out some things to just pay attention to as far as how this is organized. Okay, once we've identified all that and just made sense of our graph, let's go ahead and start finding the areas like we did before. The first one, it's color coded in green right there. So in order to find the height of this green rectangle, we need our function. Let me just again remind you, the function is y equals x squared. And by the way, like we're gonna have different functions, but I'm just using x squared just to like, stay with the same function. So it's not as difficult when we're learning this. Okay, so here's the first step. So once you know your function and once you know what input you're gonna start with, you're gonna start to plug in that input into your function. So because remember we started at the first upper right hand corner, which corresponds to 1.5, that means we're plugging in 1.5 to our function. 1.5 times 1.5, you can use a calculator, you get 2.25. So that means, let me draw a line, that this first upper right hand corner has these coordinates right here. After we find out that, right, we have the height, we have the base, it's 0.5, then we know the area of that green first rectangle is going to be the base times height. You multiply those two together, you're going to get this as your answer for the first green rectangle, 1.125 units squared. So let me just pause here to see if anyone has any clarifications on the first rectangle or anything like that. All right, cool. Let's go on then. All right, so now for the next rectangle, the next upper right-hand corner corresponds to 2. And I'm going to also color code that as red. And so that means since the next upper right-hand corner, if I like make a line down to the x-axis, that corresponds to 2. So I'm going to take 2 and I'm going to plug it back into my function. So that's going to get me 2 squared, which is equal to 4. Awesome, we have this coordinate points then. So the second upper right-hand corner of the rectangle is at 2, 4. So then what we're going to do is we're going to go to the side and calculate the area of that red rectangle. Base 0.5 times height 4, we get 2 units squared. And again, I'm using unit squared because it's area. You don't have to use this because right now for this function right here, we don't have units. We don't have like a rate, time, it's just a general graph. All right, we got 2 more rectangles to go. And again, I'll be pausing if anyone has any questions or feel free to use the chat. Let's do the third rectangle, and I'm going to color code that in blue. And then notice that the upper right-hand corner, if you make a line down to the x-axis, corresponds to the input of 2.5. There's the subscript, but let's go ahead and plug in 2.5 again into our function. So we get 2.5 squared is 6.25. That's going to give me coordinate points of this right here. Same process, so we're going to do base times height, and you should get 3.125 units squared. Then we'll do our last one. So last one, I'm going to color code as purple. So same thing, we're doing the same process. So this upper right-hand corner corresponds to this x value of 3. So that means we're going to take 3, plug it into our function to get the height of the rectangle. So I do that, 3 squared is 9, 3 times 3 is 9. So then that's my last coordinate point that corresponds to the last upper right-hand corner. So all I gotta do is now find the area of that purple rectangle, base times height. All right, we got 4.5 units squared. So I got all the areas of these rectangles. Don't forget, we're gonna take them all and add them together. We're gonna sum them up. Adding them up, that gives us 10.75 units squared. So I'm just gonna pause here because we're gonna have a participation check in a second. So before I move on, I'm just gonna pause to see if we have questions, clarifications, anything like that. All right, let's see. We got a chat thing. Let's take a look. Oh, sorry. You added the 4 units to get the final unit. That's correct. So there was a clarifying question. All right, cool. Thank you for the clarifying questions. And now I want to also, let me delete my, I'm going to ask you all a question, and that's going to be a participation check. So before I leave this, I want to kind of just go back and show you our comparison, because we first did a left Riemann sum, then we did a right, and we had 2 different approximations for the area under the curve. This one we got was 10.75. And if we go back to yesterday or 2 days ago's work, we got 6.75. And remember, we kind of discussed that this right here was an underestimate because of the white space that we didn't take into account, right? It's not actually the true area under the curve. This right here was an underestimate. Now we have this right here. And in the participation, don't answer yet, so don't answer in the chat because you're going to do that in the participation. I'm going to ask you, is the sum of the rectangles that we got, 10.75, is that greater than or equal to the actual area? Is the first question. The next question is, how can we use Riemann sums to make a better approximation? So that's the questions that I'll have you do on this participation Google Doc, and this will be for credits. You want to make sure you fill it out. Let me share it with you all in the chat. And we have about 23 of us that are in here, so there should be 23 responses. So again, in order to get your credit, you could put either your initials or you can put your name if you don't mind, you know. But if you don't want people seeing who you are as you're typing, you can go ahead and just put your initials so that I can give you credit. So let's open this up. Again, the question is there in yellow. Great, I see a lot of us getting in there. We should have 23 opening up the document. We have 9 right now. 9 probably including me. If your name's not on here, you want to make sure you get on here. Right, we got 15. We still need a few more of us on here. Okay, we got 17 total. I think we still need, okay, we got 18 now. We need 5 more people. 5 more people that need to make sure you're in this document that's in the class right now. So we need 4 more. Okay, so this is going to be your credit. All right, so I'm just encouraging everybody to get on in here because I don't want you to miss opportunity for this credit. So please, if your name is on here, you're good. Make sure that you're on this document because you want to make your contribution. So again, you're either going to put your initials or your full name, and you're going to go ahead and attempt to answer this here question. Is the sum greater than or equal to the actual area? Second question is, how do we use Riemann sums to make a better approximation? The last one I added here, if you're stuck, right, put down a notice or wonder. So this gives the opportunity for everybody to get credit. I don't want anyone to miss out on any credit. Awesome. Let me give you all like 2 minutes. Let's take a look at this. And then let me also update attendance. All right, let's take about 1 more minute to finish up our thoughts on this question. About 1 more minute, and then we'll take a look at what y'all are thinking about answering this question or what notice and wonders y'all have. All right. And if you're done, go ahead and take the time to take a look at what everyone's saying. Again, you want to make sure that you are that you put your name or initials for your credit. All right, so we're getting that the area is bigger, and then we're finishing up a because there. Awesome. I think this would be greater than the actual area because maybe the rectangles are greater than the original. I think to find the accurate, we want to combine. Ooh, that's a good idea. So there's an idea there, like on how to use Riemann sums to make a better estimate. This idea right here is find an accurate estimate, we would combine both the left and the right. Maybe kind of thinking of an in between. That's a good idea. All right, what else do we got? I would say it's greater than. So a lot of you are agreeing that this is the area of the rectangles is greater than the actual graph. And it says because it makes up more space than the area, it's moving past it to the height of 9, specifically is what this answer says. I notice it goes up at least one unit each time. So it's definitely like more than the actual true area. And the formal way we say that is an overestimate, just in case y'all want to know the formal way. Yeah, I'm seeing greater than is like the common phrase here. Awesome, awesome. Yeah, another way to say it is that the area of the rectangle goes over the line. That's a good way to phrase it. And y'all can take a look and just see if any commonalities or anything that's different. I'm trying to highlight what's different, but I notice a lot of similarities. Everyone's mostly agreeing that the area of these here rectangles is greater than the actual true area. Yeah. Notice that the rectangles are longer than from the one before, and noticing that there's kind of like triangles that are outside and above the curve. I noticed that too. And then I wonder if you did the opposite, would the sum be the same? Mm. All right. Yeah. Thank you so much. Again, make sure that you put in either your name or initials for your credit on this document because I'll be checking it right after class. Thank you so much for your ideas. Again, super valuable to make your thinking public because y'all are noticing like the difference in thoughts or the similarities as well, and it also solidifies what you were thinking about. So it's super important to take a look at all your thoughts. So we're going to go ahead and move on from this. Again, you'll be getting credit. Do not worry about that. And I need you to get ready your notes because we're going to move on to the next portion of our notes. It's going to have a new title, new learning target. Let's be ready. So here is the new title and our new learning target. The title is, so now how are Riemann sums connected to sigma notation? If y'all remember, like kind of like, I think it was the second day of class or something, we started talking about sigma notation. Sigma notation is like that funny symbol that looks like this. And it also showed up in your homework a bit after that. We're coming back to sigma. So sigma is making a return. And we're trying to see how are these rectangles that we drew connected to sigma. So the learning target is I can connect Riemann sums to sigma notation. There's going to be like a group Google quiz on this afterward as well. So you want to make sure you take your notes and you pay attention. Let me give you all some time to write this down.
Is this gonna be complicated to do this? The Riemann sum to sigma notation.
It depends how you think of complicated. So some people already think Riemann sums themselves, you know, the whole process I just showed you all. Some people think that's already complicated. So it depends on your perspective. Yeah. Yep. Some new people joining. All right, just a few more seconds to get this down, everybody. Also, for those that just jumped in and weren't here present at the beginning, welcome. All right, let me mute. I keep hearing myself echo. There we go. Um, we did a participation check right now. So if you came in, if you could private message me so I could give you that participation thing so you could get your credit. And we're taking notes, so let's all be ready for this. Well, and yeah, well, I'm stretching because, yeah, I mean, the ideas themselves are gonna be, you know, we're heading into calculus territory, so it is a mind workout. I'll say that. So let's just prepare our minds for that. All right, cool. Let's move on. So I hope you all got down the title and the learning target. Let me go ahead and erase this. Let's go. Let's do this. Okay. All right, so first we're going to review. So because we're going to be talking about how to connect the rectangles we drew to sigma, we're going to review how to do sigma, right? It was a past learning target, but it's always good to have like review. It's not like I expect you all to 100% remember it, especially if you haven't yet had access to our big ideas packet. Don't worry, that's in the process of being made, but let's review this. So go ahead and copy this down. We're going to review how to do, how to construct a sigma notation given a sum. So here's our sum, and here's our steps. So remember, I kind of went over these steps with you all. Step one is to create a rule or function based on the pattern that you see. Step two is you make sure you test out your, if your pattern works. Step three is decide on the correct index. That's the starting point at the bottom. And then number four is decide where the upper limit ends. The upper limit is the number at the top. So those are our steps, and we're going to follow them. Step one, identify pattern. So maybe someone in the chat, can you let us know, like if you already see a pattern, what is the pattern you notice that these numbers are kind of like doing, or what are these numbers doing? What's the pattern? Let's see our chat. Yes, Jayla and Shaylin both are saying you see that +3. I have another one in the private chat saying it's +3.
Going up by odds.
And going up by odds. Yes, that one's true as well. Okay, so we got this. So we could think of this as either going up by odds, or wait, odds? I don't know if 6 is odd though. Almost by odds.
Odd and even. Odd and even. My bad.
Yeah, odd and even. Yeah, you almost got me though. I was convinced almost, so it's okay. All right, so yeah, we noticed that it's going up by +3. So I don't know if you all know this yet, but when it's going up by +3 each time or plus anything, the formula will be multiplication. So it's actually going to be this 3, it's whatever number you're adding each time, times n. It's going to be 3 times n. And if you kind of think of it, multiplication is like addition each time, except, like, like for example, if you add 3 times, that's the same thing. That's the same thing as you doing 3 times 3. So multiplication and addition strongly related. Some people might have tested out this one though. Some people might say it's this one, n plus 3. But if you test this out, it won't work. For example, if you substitute 0, sure, you get 3. You get the first number, cool. But if you substitute the next whole number, the next integer, if you plug in 1 into here, you're going to get 1 plus 3, which is 4. I do not see 4 here, so this one does not work. So sometimes you're going to get stuff that doesn't work. That's why you got to do that second step, which is test. Test out that the rule you made works. So this does not work. I'm going to take that out. Let's delete this. And let's test this one in case you don't believe me. So usually, again, when you're adding, like the way we are +3 plus 3, it's going to be multiplication. So let's check it. So let's start substituting some values for n. So in order to get the first 3, I think what I got to substitute first is n equals 1, because 3 times 1 is 3. So that works. I'm going to put a check mark right here. That works. Then we could check the next number. The next integer is 2. If I plug in 2 for n, it's going to be 3 times 2, which is 6. So the next number is working out. Maybe I'll just check it for one more, because then otherwise I feel like we got the function. You don't have to check it for every single number. If we plug in the next integer number is 3. If we plug in 3 in for n, you're going to get 3 times 3, which is also 9. So yes, I think this works. So basically the pattern is, and let me write it right down here, if I plug in n equals 1, I get 3. If I plug in n equals 2, I get 6. Plug in n equals 3, I get 9. N equals 4, that's 12. N equals 5, you should get 15. You could test it out. And n equals 6, you get 18. So it helps to kind of just put this there at the bottom, but you should, verify. But yeah, I could already tell that I will get these numbers. So that means once we have the rule slash function, this is the rule slash function that we agree upon after testing, then we're going to be ready to get started on creating the sigma notation. So you're going to draw your big old sigma like this to the best that you can. And then what goes right here after the sigma is the rule slash function that we agreed upon. It's 3n. And then at the bottom, step 3 is we need to decide where the correct index starting point is. This bottom number right here is the index. So the first number we plugged in was what for n? Let's see the chat.
1.
And I heard a 1. Thank you so much. Yeah, and then that big E is your sigma. You could totally do that if you're typing out your work. I would understand that. And then Shema also said 1. Yeah, you guys are correct. We start with 1. And then where do we end up at though? So where do we stop? Where do we stop here on n when we're plugging in?
6.
6. Perfect. 6 is the n value that we stop at. Yes. Perfect, perfect, y'all. So let me write down that 6. So 6 just goes at the top. We just don't write n equals 6. I don't know why. That's just the way we do sigma. We usually start the index by saying variable equals blah, and then we put the ending input up here. But that's it. So we've created our sigma expression that represents this here sum. So that's just a review on how to do that sigma expression stuff. Let me just pause here for any additional questions. Or like for you to copy this down a few more seconds. Then we'll move on to now making the connections. So this right here was a review. All right, cool. Let me go ahead and clear these drawings so that we can move on to now the learning target. Remember, we wrote down that our learning target was to make connections between that Riemann sum stuff, the rectangle stuff we were doing, to sigma. So let's see what that looks like. Okay, so what I have for you here, you don't have to copy this down because this is from Monday's notes. So I just took a screenshot of our notes and I plopped it on here so we could kind of analyze what we're doing and how it connects to Riemann. Oh, sorry, let me mute. There we go. Okay, so first thing I'd like you to notice, and if you remember, the first step to creating a sigma expression is to notice the pattern. Like, what is the pattern that's happening? And things to notice is that, let me change my color. Things to notice is that we always are multiplying by that width. Whatever that width is, we're multiplying that by. That's a pattern I'm already noticing. Another pattern I'm noticing is these numbers right here. The second value are the y value heights, which came from here basically. Now these y values can be represented using this here subscript notation. So this is the part that might, that might bring about some questions. So for this left endpoint Riemann sum, the first point we plugged in is going to be 1, right? But that corresponded to x sub 0. So the first output is the same thing as saying plugging in f of x sub 0. And that's how we're going to kind of just create our patterns. You'll see. So let me just stop writing. So that's just the general thing. So I noticed that there's a common width we're multiplying by. I also noticed we're multiplying by the heights, which is our function output when we plug in. So let me draw some arrows here. So right here, remember I said that was rectangle heights. And how we could think of the rectangle heights as f of, and then we're plugging in whatever subscript we started with. That's why we labeled that bottom part, so that we could identify like which subscript are we plugging in. So that's where the labeling comes in. So this right here is rectangle heights. Next. The next pattern was, of course, the first one I pointed out, the fact that we have these common 0.5s. There's a specific way we write the width of the rectangle, and it's called this. It's right here. The rectangle width, we call it in math as delta x. That's how you read this triangle right here. Or you could say change in x, whatever. But the rectangle widths are going to be represented by delta x. So that's just a new term for y'all. So 0.5 is our delta x right here. So that's what we're just naming that. Okay, so we know that we're going to take the rectangle heights and we're going to multiply it with my rectangle width, right? Because that's what we do, base times height. We know this needs to be multiplied together. So I think we have the pattern. The pattern for my sigma, here's my sigma, and this time I was able to kind of insert an actual sigma instead of me doing a messy one. Our pattern is going to be height times width, or base times height, whatever you want to think of it. Here you see it right here. So see, this is my rectangle heights. Rectangle height. Oh, well, I can't write it all. Rectangle height. Heights with an S. It's like all of them. Because it has this x sub n, that means n could be, it could be 0, it could be 1, 2, 3, or 4. And then this right here, this right here represents our widths, our rectangle width. In this case, it was 0.5. The widths. Now, the only other thing we need to, think about, and you probably see it popping down right here, is where do we start when it comes to a left endpoint sum? So this is the part I really need to explain. because you might have questions on it. So where do we start? So for a left Riemann sum, remember we started at the upper left-hand corner. That was for left, upper left-hand corner. And the upper left-hand corner corresponds to the subscript x sub 0. When it corresponds to the subscript x sub 0, that's where we start. So that's why we decide to make n equals 0 at the bottom, because that was the first upper right-hand corner. It corresponded to x sub 0. So that's the why. Let me just put an arrow right here so you see that direct connection. Now the last, maybe someone can use a chat. So the last upper left, so the last upper left-hand corner corresponds to which subscript notation? Maybe someone in the chat can tell us. Because once we find out what subscript notation that corresponds to, we'll know what the upper limit, we'll know what that number is on top here of the sigma. Let me just give pause to see if anyone in the chat knows. All right, someone privately said x sub 3. Let me know if anyone disagrees with that. But I definitely agree, because if you see that I drew my line down here, it pointed precisely to x sub 3. I know it's kind of hard. It might be tiny if you're looking at this, but we do have this in our notes. So if it ends at x sub 3, that means my upper limit, that number up here, is going to be 3. And oops, why did I write it? If I already have it, look, take a look. There we go, it's 3. So this right here is the sigma representation of the left endpoint Riemann sum. There is another way you could kind of write this if you write it like this. So saying everything else is the same except for the fact that I replaced that delta x with the 0.5. Because in this case it was 0.5 always for the base of the rectangles. So you could write it as either ones, and they would both be what is it called? Proficient to me. All right, let me just pause for any questions. But that is how you connect. So that's like kind of connecting all the stuff we're learning. How do you connect sigma to the rectangles? And, you know, how does this represent what? So there's our connection. So it's a humongous big idea right here. And then the next slide, I'm going to talk about the right endpoint Riemann. I'll just pause here for questions. Again, you're not copying down this whole chunk right here. You're just mostly copying down the sigma because you already have this down in your notes. Okay, cool. Let me clear up my drawing so we could head off to the last connection to Riemann sum, which is the right endpoint. Clear my drawings. And again, it's okay if your brain hurts right now. It's expected. Now, we just did the right endpoint summation. So we did this and we all knew, we all agreed that we got an overestimate. And we want to still kind of create that sigma representation. So again, I'm going to label this the same way I did before. Again, we still have our rectangle heights. They're going to be f of x sub n. It's going to be the same, except in this case, we're looking at the upper right-hand corner. So this one, in our sigma notation, is going to start at 1, because notice the x sub 1. And it's going to keep going. I'm circling the upper right-hand corners now. It's going to keep going, and for our sigma notation, for the number at the top, it looks like it stops at 4. So that's just going to be some differences we're going to see in a second. Again, I'm going to point out for this particular problem, we again had that the base was 0.5. We call that rectangle width as delta x right here in yellow. Same idea, same stuff. And again, what we do is you take the height, you multiply it by the base to get the area. That's what we're doing. That's our pattern. So that's our sigma. Here's our pattern. Now, the thing that's different with the right Riemann sum is this. Take a look. Instead, we're starting at n equals 1 because we started with the first subscript, x sub 1, instead of x sub 0, like in the prior problem. So we started here. That was the first upper right-hand corner. And our ending number is going to be what? Let's see if anyone knows here in the chat. for a sigma notation? What's that number that goes at the top? If you look at the visual and try to make that connection. Yeah, awesome. I'm very impressed. So Shaylin put X of 4. We have a private chat, which is correct, as 4. Jesene, you put 10.75. That's the area. And I have another one saying 3. And then you're like, wait, never mind, Jesene. Okay, that's okay. So the correct answer out of all of these is the number that goes on the top is the number of the subscript. So the last upper right-hand corner is right here. This is the last one, right? Last one, last one. And that corresponded to the subscript of X sub 4. So the number that goes above in the sigma notation is 4. It's this 4 right here. So boom, and then that's going to be basically the end of your sigma. Yeah, and a lot of you are like, asking me private chat questions and so forth, and some of you are getting it. I'm like, yay, that's okay, because it's a challenge. I'll say that. Again, you can rewrite this like this if you desire. Again, it's the same thing, except I replaced the delta x with 0.5 because for this particular, it was 0.5, and that's it. This is our connection. This is how you represent Riemann sums with sigma. It's, it's wild. I'll pause here for any additional questions, clarifications, things like that. Yeah, and then I'm gonna end up right now with kind of like what was the big ideas of what I just did right now? Like what are the main things you should get from this connection to sigma in a second? And then we're gonna have our checkout question. So that means basically our group Google quiz on what I just talked about is going to be happening on tomorrow, Thursday. So I'm going to be putting you into your groups. Remember your usual assigned groups, and you'll be trying to make sense of what we just talked about together and entering that together in the Google form. So that means there's going to be like 4 names in the Google form, and that's going to be like everyone will get their credit that way. And that's going to be for Thursday. So just as a heads up of what's happening. All right, let me clear this. All right, so after all of this, we noticed basically, I don't know if you noticed, the sigma notation for the left and the right basically looks super similar because both of them are doing base times height, right? They both are doing this f of x sub n times delta x. So this is the main takeaway. This is our big idea. The difference between the right and the left Riemann sum using sigma. So here it says K represents the number of rectangles. So basically, y'all notice that for the left Riemann sum, you had, it was the upper number was less than the one with the right Riemann sum. For example, in the left one, the number was 3 and it started at 0. And for the one on the right, it always starts at 1 because that's the most right. It's the first upper right-hand corner that corresponds to the subscript notation. And this right here would just represent the number of rectangles. So what this means though, when it says K represents the number of rectangles, like in that problem, right? Let me just draw it. We had 4. I don't know, 1. I know I'm doing this messy. We had 4 of them, right? 4 rectangles were under our curve. So for the left one, what we do is K minus 1. That means if you have 4 rectangles, then you know it has to be 3 if it's a left Riemann sum. And it always starts at 0. Then over here, always starts at 1, and the K number is the number of rectangles. So because there was 4 here, this is going to be 4. The number of rectangles, it connects to that. So that's the only difference actually. The only difference between a left and a right is basically their starting and ending points. The only difference between the two using sigma notation. So that's just a humongous big idea. You want to make sure you write this down. And then we'll do quick checkout. I'll give you all a few seconds on this one. And then of course, we're gonna review it on Thursday and we're gonna have our little Google form quiz on it with groups. And this one, yes, I want to grid on accuracy. That's why I want you all to be in groups so that you're not afraid. You could talk about it to each other, work on it together. All right, y'all, quick checkout. Thank you so much for, your thoughts. I love like all the stuff on the Google Doc and whatnot. But here's our checkout question. Just one thing, because we talked about a bunch of connections, right? What's one understanding you can make between Riemann sums, that's the triangle stuff, and sigma notation, that's the sigma E stuff. So let me just write it like this. So that's E. Riemann is basically when you do the rectangles under a curve, just so that you all can get a visual of the terms and what they mean. So just one thing in the chat, what's one understanding or one connection that you can make between Riemann sums and sigma? So go ahead and use the chat for that checkout. Or, of course, I want to open this up. If you're like really just confused, you could put a notice or wonder. That's totally fine too. Yes. All right, here's our first checkout. They both help you find the area of each rectangle. Yes, that's true. You could use the sigma or you could use the Riemann sums and do the calculations for both. They would both give you the same answer, yes. That's an awesome understanding. What else do we have? And again, it could be notice or wonders. You can't be wrong with this. All right, we got a few coming in. And I'm getting these privately and some are towards everyone, but let's see. One connection is that it helps you finalize. I notice that they're set up different. Yes. I wonder how far their similarities will go and help you. The connection is that they connect to the same equations. They could possibly relate to when you find an area. A guess, to be honest. That's actually not a guess. That's gonna be how we're gonna use this. I wish you said that publicly, but that's okay. One thing I understand is that you give the area of the rectangle. Yeah, usually it's given. The calculations you would do with the graph is incorporated into the sigma notation, but they're written differently. That one like really blows me away. That the one I just read. Wow. Riemann rums and sigma notation will get you both the total area under the graph. Yes. I even spelled it as rums, so it's okay. I noticed that once you get the y and x values for the rectangles, it gets easier to solve. And they both give you the area. Awesome, y'all. Thank you so much for again, I'm getting a bunch of these in, and sorry if I didn't get to read all of them, but they're all really, really amazing. I kind of wish I made a Google Doc for this one. Yeah, if you could connect both, find the area. I understand that sigma and Riemann are both ways to solve areas or solutions. And then there's a great wonder. I wonder if you could use one equation and check your estimate with the other. Sigma will give you the total area I need to join office. Oh, okay. Then I need to join office hours because I need to understand it a bit better. Yes, office hours for sure. I'll be here waiting. It's been very busy in office hours. I appreciate all y'all coming in. All right, y'all. Thank you so much. It's been a great class. Bye, everybody. I hope it wasn't too much of a brain.
Bye.
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 Bye. Hope your brains don't hurt that much. Bye, everybody.
I have a question.
Oh, yes. Go ahead.
So what did you mean about the left and right for the the left? Yeah, that one.
On here? Yeah. I don't know if you noticed. So for example, when I did, so this one's right. Where's my left? Where'd it go? Oh, that's my future. There we go. So we first started off by writing the left Riemann representation, right? So we started with the sigma notation for this one, right? And I want you to notice that this is going to be the same as the other formula, except notice how these numbers are going to be the only difference between the two. So this one starts at 0 because first upper left-hand corner, because this is a left endpoint sum, corresponds to x sub 0, corresponds to this. So that's why we start at 0. So that's why we always start at 0 here. And then the last upper right-hand corner corresponds to x sub 3. So that means the number at the top right here is 3. So that's where we stop. And then I kind of just made the equivalence there. Mostly important is this part. So that's that, right? Let me go ahead and clear that. Let me know if you have questions on that part though. Any questions on this one?
No.
Let me clear drawings. Okay, let me go to the next one now so you could see the difference. So same idea, right? We still have our heights. We still have our, yeah, it's the same thing except the starting and the ending for the sigma are different for the right Riemann sum. So it's different because for this one, the first upper right-hand corner is right here. That corresponds to x sub 1. So that means we have to start at 1. And then the last upper right-hand corner corresponds to x sub 4 right here. So that means we need to end at 4. So that's, yeah, the only difference is the start and the ending point of the left and the right. So that's just the only difference between the two. And then how that slide looks like. I know it's like confusing because there's a K in there.
So it basically is like what corner touched the line?
Yeah, and then you could see where it starts and where it ends, like to create your sigma. But here it's kind of like general. Whenever you have a left endpoint Riemann sum, you're gonna always start at 0. It's just always gonna, because that's gonna be your first left endpoint. Like the first upper left-hand corner is always gonna be at 0. Then you always are gonna end at number of rectangles minus 1. So remember, like right now we looked at the rectangles. We had 4 rectangles, right? But if you subtract 1, you get 3. So that's how we had that 3 from before.
Oh, okay.
And then this right endpoint starts at 1, and here it's just k. That means you don't subtract. That means there was just 4 total rectangles. So this top number is 4. That's the only difference between left and right, is where the sigma starts, where the sigma ends. But yeah, so that's the difference. I hope that makes sense.
Yeah, it makes more sense because like I don't know what she meant about left and the right, but now I understand it.
All right, yay, awesome, that's great.
Okay.
Yep, thank you for asking. All right, I'll see ya. Bye.